Morning, everyone. So far we've been looking at some KSP problems. Basically, there's two ways of making a saturated solution. One way is dissolving in solid, where the ion concentrations will follow the mole ratio. The other way of making it is to mix solutions together. Sure, we need to do two dilutions, C1V1, C2V2. We'll see that a little bit more in this lesson here. Because the cation and the anion may come from two totally different places, it may not necessarily follow the mole ratio. So just look out for that. Sometimes the ions, they match up to the ratio, sometimes they don't. When you get those ion concentrations, you can directly punch them into the KSP expression. We always put the solid on the left side so that the KSP ends up being divided by 1. We always ignore solids, and therefore I can just refer to it as a solubility product constant. Today we're going to flesh out a little bit more. The KSP is actually going to be a nice value for us to hit, that if I'm lower than this KSP, even if the ions were supposed to be low soluble, I'm going to find that there's actually not enough ions to actually react together to actually end up precipitating out. When I hit KSP, that's when I'm in equilibrium. That's when your precipitate just forms. You've just hit the solubility limit. Or we're going to test it. Maybe my ion concentrations are way higher than what it should be at KSP. For shifting the equilibrium, I'm going to actually need to precipitate out. So I'm actually going to use KSP as a nice test value. We're going to learn this section here in terms of a trial ion product. Really, I just want to link this to something that you're used to already. So this is trial ion product. You can write TIP for short, trial ion product. I'm going to give you the definition first. I want you to tell me what this sounds like. It's the ratio of products to reactants at any time. And usually that any time here is the initial values, right? Well, we've seen this before, right? I've done concentration of products over concentration of reactants. In general, if we were using the equilibrium rule, we would call it KEQ. But now what they're doing is they're implying, well, I'm just going to test it. I'm just going to try it out. Maybe test it out with initial values. Test out the ones that are on the I row. Well, that essentially is basically from the last chapter, especially when we were doing ice tables, when it wasn't really sure which side is plus, which side is minus, we had calculated a Q value. A Q value was sort of a test or a trial KEQ, and basically this trial ion product here is going to be a test KSP for us. And we're going to use this test KSP here depending on what this Q is relative to what the KSP is supposed to be. This is actually going to tell me whether a precipitate forms or doesn't form. Okay. So let's just do this really generically here. Let's say I start off with 2 beakers. I'm going to mix 2 solutions. Let's start off with an AB salt. This one here is aqueous. Whenever it says aqueous, even though it's shorthand to actually put them together, aqueous means water has separated the positive from negative. For simplicity, let's just say A plus and B minus. I'm going to toss that in together with another container. The other container has its own volume. Let's say this is CD, aqueous. The charges may actually be different. Maybe this is C plus 2 and D minus 2. Totally possible. Right? It's still just a 1-to-1 ratio. But being aqueous, water has separated them. I toss them in together, and we're going to end up in some third container. Remember, just right from the start here, there is a dilution. So both solutions are diluted into the total volume. And for a dilution calculation, remember later on you're going to do a C1V1, C2V2 for the AB salt. You're going to do a C1V1, C2V2 for the CD salt. All right, so that's already given. Okay. So now what's going to be implied here is you just toss these together here. The A plus and the B minus has been transferred in. The C plus 2 and the D minus 2 have been transferred in. Now what I want to check my chart for is check for any low soluble things. Check for things that might end up solidifying out. For argument's sake here, let's say I check my salts here. Let's say A plus was fine dissolving with B minus, but maybe A plus and D minus, they really don't precipitate. They really don't like being dissolved, so they precipitate out. So because of the charges here, that would actually be A2D, right? I need plus 1, 2 of them to counterbalance the D. Let me just write this out for you here. Assuming that you've done your dilutions, I'll walk you through a worked out problem later on as well. But let's just try it out here. Our reaction involves now, it's AB reacting with CD. I'm predicting it to be a double replacement reaction. We just said it's going to be A2D. Just looking at the charges, A is plus 1, D is minus 2 here. Once you work out the charges, don't show the charges anymore. And then to finish off the double replacement, the other case is going to be between C plus 2 and B. So this is going to be C, B2. Right? And again, for argument's sake here, these ones here are aqueous. We had been under the impression that, let's say A2D is the thing that's low soluble. This is the thing that dissolves the worst. This is the thing that not only do we say is a solid, this is a precipitate. This is the thing that crashes our solution. It used to be fully clear, and suddenly when you put them out together, it suddenly crystallizes out as a solid. CB2, just for argument's sake here, let's say it's aqueous. When we did this ionic stuff here, it was possible that both of them were solids. Just to simplify the math, we're only going to deal with one solid at a time. This is going to be a general rule. Once you identify what the solid is, back when we did a mixing question, C1v1, C2v2, we had assumed that the particles don't actually care each other there. This time they actually do, because as the A swims around D, they realize if their concentration is high enough, they're actually going to solidify out. With that precipitate, I'm going to put the solid on the left side. So I'm going to have, let's say, A2D, solid on the left side, even though technically it was a product of my ionic equation. So I have A2D, I'm going to end up getting 2A plus, and I'm going to get D minus 2. Those are my ions. I'm going to write that expression. I'm going to write the KSP expression. The KSP expression will be the ions. The coefficients go up into the powers, A plus squared, and then we have the D minus 2 here. Question in this problem, we saw two ways of making a saturated solution, as I alluded to here. Will the A plus and the D minus 2 in this situation, will it follow the mole ratio? Well, let's ask ourselves, where did it come from? The A plus, it came from our solution AB. The D minus 2 actually came from a totally different solution. It came from CD. There was nothing that said, if this one was like 1 molar, oh, the other one has to be a certain molarity. These are two totally different mixtures. You can mix in whatever molarities you want. In this case here, because we're mixing solutions, again, the A plus and the D minus, mixing solutions means it doesn't follow the mole ratio. So what I'm going to do instead is I'm going to do that C1v2, C2v2. I'm going to calculate for myself how much A did I get from the first solution, put that number there. How much D did I get from the second solution upon mixing, put that number there. And there's no guarantee it's going to be 2-to-1 ratio. However, if you know those numbers, those are the placeholders we have already hit equilibrium, you can always sub those in directly. Yes, you will still need to end up squaring the A because that's a totally separate equation. Right? What I want to show you here is, yes, no doubt the A2D is the low soluble one here. Whenever this concentration gets to be high enough, it's actually going to precipitate out. Let's do our test value there. If we do our test value, I'm going to call it Q, you can call it TIP if you like. If when I mixed in these amounts here, A, B, and CD, even after the dilution, after the mixing, if it perfectly matches out where the A and the D, when I multiply them, if the Q perfectly hits KSP, my trial value is exactly what it should be at equilibrium. This one here tells you my solution is currently at equilibrium. You just managed to be really lucky, even though you're not following the mole ratio. You just added in the right amounts of A, the right amounts of D for what it needs to be at equilibrium. Remember, at equilibrium, we would have just hit saturation. We would have added in, at first when you added in these two chemicals here, if the concentration, if the numbers were too low, it actually wouldn't precipitate yet. But I'm at a test value where my concentrations A plus and D minus, they're high enough that it actually just formed a precipitate. So our conclusion at that point there, because we know we're at equilibrium, we can use that terminology, we know we formed a saturated solution. A saturated solution will have undissolved material present. That's going to be our precipitate, undissolved material. And our conclusion out of this here is we're actually going to say a precipitate, a PPT, just forms. Later on, we're going to deal with questions here. Are the concentrations high enough for a precipitated form? We basically test what my current concentrations are. We're going to test them against KSP. What if I have, so I just calculated my, how much A plus do I have, how much D minus do I have. What if when I do this multiplication, I do the A plus squared and the D minus, and what if my trial value is actually larger than the KSP at this temperature? So, what if my trial KEQ, well, I'm calling it TIP, what if it's bigger than KSP? Right? KSP is a constant, so KSP is a constant at this temperature. Right? So this is a sort of a number that is not going to change. I just test my values. When I do right now, I currently take my A plus and square it with the D minus 2. I end up realizing my values multiplied are too big for KSP. So same thing as happened in chapter 2. What has to happen is the Q needs to start getting smaller and smaller until it ends up lining up with KSP. Systems, Letelier says, it'll naturally approach equilibrium. So if Q, or my TIP, if this Q at the end of the day is sort of products or reactants, and my number currently is too large for what it should be at this temperature, I need my fraction here to go down. For this fraction here to go down, I need to lose products, I need to gain reactants. Well, if you look back at the equilibrium here, if I lose products, I'm going to lose this side, gain reactants. That means my ion concentrations are way too high. I'm actually going to force ions to solidify out. Even if, when I first mix them together, all the ions are there, I'm going to force them to actually solidify out to become a solid. We're going to just write this in words here. The system shifts left to reach equilibrium. And when we looked in detail here, going to the left means my previously here dissolved ions will precipitate out as solid. So my ions, even though the numbers currently are too big, when I just randomly toss solutions together, the concentrations were way too big here, I'm going to want to shift left. I'm going to want to bring down my product concentration until they end up hitting KSP. So the conclusion there is definitely yes, precipitate forms. Now the last case is also very interesting here. Because the A and the D, they don't have to follow more ratios, and the A and the D here just depend on my starting concentrations, it's totally possible that I started with so little A, so little D. After mixing together, the concentration is still so tiny, even though the A2D is a low soluble compound, maybe my ion concentrations aren't high enough. So when I try to do that math here, take a really tiny number squared times a really tiny number, my trial value could be possible that it's actually less than the KSP value. In that situation, again, I could say Q as well, just to get you familiar to the terminology here, I can call it TIP. What if your TIP value, your trial ion product, when you try your ions, when you try to multiply them together, what if your values are currently not big enough for what it should be at KSP? KSP here is the equilibrium constant at this temperature, but my trial value is not big enough. Well, again, my trial value, again, that's another way of saying Q. My trial value is supposed to be products over reactants. If my starting amounts here aren't big enough, I need my product over reactant ratio to get bigger. And for this fraction here to get bigger, I need to increase products and I need to decrease reactants. Let's have another look at our equilibrium expression. I'll just draw it down for you here. A2D was in equilibrium with A plus. There's two of them, and I have D minus 2 like this. In this case here, if I find that my trial value is actually lower than what it should be, the trial value has to increase. How can it increase? Is to lose reactants, gain products. It's a little bit hard because the solid has a constant composition. I'm not actually going to be able to change this number. That's why we ignore it in the expression. That's why it's a divide by 1. But definitely here, I can try gaining products. Let's force more of the solid to actually break off. And as I preference the dissolving reaction, there's not going to be any leftover solid. So that's sort of like the A plus and the D minus. There's so little of it in solution already. Any added solid, it's going to break up. Any added solid, it's going to break up. Because I want to basically beef up the concentration of A plus and D minus so that these guys, when they multiply, they're going to end up hitting KSP. So in that situation, our conclusion is going to be no precipitate. Long story short here, the KSP is always going to be a constant at that temperature. The KSP is the minimum limit that your ion have to multiply to give before you hit precipitate. If you hit KSP, a precipitate just forms. If you're over it, you'll definitely form precipitate. Any leftover ions will crystallize out. If in this situation my trial value is less than KSP, even though A plus and D minus 2 is supposed to be low soluble, it's supposed to form precipitate. Maybe my concentrations are just not high enough. I still need to beef up my products. The only way for you to get more ions is for any solid that you add to actually break up. Any precipitate or any solid that I toss in extra will just naturally break up. No precipitate will form. I need to, at the very least, be at the KSP limit before precipitate forms. Okay, so that's the sort of overview here. Let's walk through a question. This question, they're going to be worded in this style here. Does a precipitate form? Are the concentrations high enough when I mix the following solutions? Does a precipitate form when 15 milliliters of 0.300 molar zinc nitrate is added to 25 milliliters of 0.430 molar strontium hydroxide. So that's the question, and I'm going to give you here, given the KSP for this compound, zinc hydroxide, that's the solid I'm interested in this time. Given the KSP for that compound is 4.1 times 10 to the negative 17. Okay, no units or anything. There's the question. Okay, again, I encourage you just to pause the video so you can try it out for yourself. Right. If the KSP is not given in the question here, we can check our solubility chart. I just checked it there, so this value is not there, so that's why they had to give it to you directly in the problem. Yes, I know at the end of the day, your answer is just yes, precipitate forms, or no, precipitate doesn't form. You are not going to get the mark if you just guess, okay? You have to demonstrate to me, well, after the dilution, what are the concentrations? I need to test what's my trial value here. How does it compare to the KSP? Is it bigger than, so precipitate forms? Is it too low that precipitate can't form? I need to do that to justify it, okay? So, as always, I like starting off with a picture if I can. We're going to begin with zinc nitrate. We currently have 15 milliliters. The concentration is 0.300 molar, ZnNO32. I'm going to toss that in together with another solution. The other solution is slightly more volume. These are totally different mixtures, so the volume is totally up to me, even concentration is up to me. There's no reason for the mole ratios to be satisfied. Strontium hydroxide. I'm going to toss them all into some middle container here. Easy question first. 15 and 25, they give you a total volume of 40. So first thing that's going to happen, even before you calculate KSP and whether we hit the trial value or whatever, first thing you want to do is the mixing, the dilution part. So let's just try that here. Let's go with C1V1 and C2V2 on the left-hand side. Let's do the same on the other. C1V1 equals C2V2 for the red solution there. Let's just punch our way through. If I have a 0.3 molar concentration, that's my starting concentration of the zinc nitrate. I start off with 15 milliliters. What's the new concentration now that the total pool is actually 40 milliliters? Similarly, on the other side of here, we have the concentration started off being 0.430. My starting volume was 25. What's the new concentration now that my total volume is 40? They're basically in this pool altogether. Any zinc nitrate is now in the pool. Any strontium hydroxide is also in the pool here. So let's calculate our starting concentrations first. So I have 15 times 0.3 divided by 40. I'm getting here 0.1125, so 0.113 molar. Notice that that concentration has dropped. Similarly, on the other side here, 0.43 times 25 divided by 40. The concentration here is 0.269 molar. Right? Now, to be sure, this concentration here is referring to SrOH2. The other concentration here is referring to ZnNO32. Remember, for these questions here, we're usually just interested in one precipitate forms. So you could do a double replacement here. Basically, nitrate salts are always soluble. You can check your chart. This is aqueous. The strontium hydroxide, checking your chart here, is also aqueous. So the possible other combinations that we can have are strontium. Is it good swimming around with nitrate? Well, nitrates are always soluble. That would definitely be soluble. What I care is actually the combination, the zinc from the zinc nitrate runs into hydroxide, and we end up realizing zinc and hydroxide are low soluble. If their concentrations get to be high enough, the precipitate will actually form. So all I really care here in this situation, the zinc nitrate has that counterbalancing negative ion here, but I'm just going to break up the salt here. The strontium hydroxide, I'm going to ionize, dissociate the salt here. So if I know that the zinc, the new concentration diluted is 0.113, that means I get 0.113 molar zinc. I do get 0.226 of the nitrate as well, but I don't really care about that, so I'm just going to track the zinc here. I just care about the hydroxide here. The strontium hydroxide was 0.269, 1 to 2 ratio. How much hydroxide would I end up getting here? The 0.269 times 2 gives me roughly 0.538 molar. Again, yes, definitely it'll end up forming strontium, but who cares? I don't really need that strontium in this question. Because they've sort of hinted at, well, the KSP that you're going to need is going to be for this compound, they're hinting at already. Potentially the precipitate that might form is the zinc from your green solution runs into the hydroxide from the red solution and precipitates out as zinc hydroxide. Whenever you identify what the solid is, I want you to write out the equilibrium for that solid. So solid on the left side, even though it was a product in this double replacement reaction. Solid on the left side, it's in equilibrium because we've just hit saturation. Zn plus 2, 2-hydroxide, and I'm going to write out the KSP expression. The KSP expression is going to be zinc times the hydroxide squared. In pretty much all the questions we've done up to this point here, we've always been saying, well, oh, I just managed to hit this. I just hit saturation. We already knew we're in equilibrium. This is one of the first times that we're seeing we may not be at equilibrium right now. I just randomly tossed in zinc. I randomly tossed in hydroxide. Maybe my concentration is high enough, maybe not. So what we're doing here is we're trying to test whether they're high enough or not. Because the zinc came from one solution, 0.113, there's no reason why the hydroxide needs to be in mole ratios. So hopefully I've emphasized that enough here. Because I'm mixing two solutions, the concentrations don't follow the mole ratio in a mixing. Right? Zinc came from the green solution, the hydroxide was something totally different. Notice in words here I'm telling you, the hydroxide was 0.538. Oh no, there's a 2 here. It doesn't mean double. No. I've told you hydroxide is 0.538, so I just put that number directly here. We already said it doesn't follow the mole ratio. Anytime you have these two numbers here, we would naturally sub into KSP. I'm just going to change it up a little bit here because I'm not sure whether my amounts are actually high enough. I don't know whether I'm actually at equilibrium. I'm just going to call this TIP, or you can call it Q if you like. Well, TIP is given by the zinc right now. The zinc is 0.113. The hydroxide amount is 0.538. Even though I did not need to worry about that 2 in terms of the dissociation, I do, yes, need to square it because that's the KEQ expression. So I just multiply those out here, and I figure out what is my trial value. How are my ion concentrations looking right now? So 0.113 times 0.538 squared, I'm getting a TIP value of 0.033. Let's say 327. Okay. Again, like KSP here, it should have no units. All I'm doing here is I'm trying to make a comparison. So far, as I toss these two mixtures together here, even upon doing the mix, so far the trial value in here is 0.0327. What should it be when it's at equilibrium? Oh, it should only be 10 to the negative 17 at equilibrium. That's a really, really tiny number. So in this situation, I can conclude here, my TIP value is way bigger than KSP. You can see that here. I have a value of 0.0327. It's only supposed to be 4.1 times 10 to the negative 17. Right? So what has to happen? The KSP is sort of my border, is sort of my limit. I know I'm actually beyond that right now. My Q value, my test value, has to get smaller. It has to get tinier and tinier and tinier until it hits KSP. Again, we did this earlier here. Q is a product over reactant ratio. Currently, my fraction is too big. I want the whole fraction to shrink. For the whole fraction to shrink, I need to lose products and gain reactants. Again, a little bit hard to gain reactants because that's solid, but at least I can lose products. My ion concentrations are way too high because I just randomly mix them together. I need my products to crystallize out more, and that's actually going to form a precipitate. So at first we had a bunch of ions here, just thrown, everything was happily dissolved, and they realized, wait, our trial value is way too big. They're going to start solidifying out as zinc hydroxide. So because, this is our conclusion, T is bigger than KIP, precipitate forms. So while you could have said right from the start here, yes or no, you actually have to go through all this math here so you can actually verify for me, does the precipitate end up forming or not. All right? I'm going to give you one more example of this just to rehash this. So when 100 milliliters of 4.0 times 10 to the negative 2 molar calcium chloride is added to 150 milliliters of 2.9 times 10 to the negative 2 molar sodium hydroxide, NaOH. I want to ask the same question. Does a precipitate form? Right. Again, the potential salt that gets formed here, it's not on the KSP chart, so I'm just going to give it directly in the question. If it's not given in the problem, you should be able to find it directly on that table there. So given the KSP for calcium hydroxide, that's potentially the salt that gets created here, is 5.6 times 10 to the negative 6. Right? So again, I encourage you just to pause the video. You can try it out for yourself here. Don't forget you have to do the mixing, the C1V1, C2V2 first. We're going to then calculate over for this trial value. If it's bigger than KSP, yes, precipitate. If it's less than KSP, no precipitate. Okay. So I'm going to work through this with you here. So we start off here with 100 milliliters. The concentration is 4.0 times 10 to the negative 2, so it's 0.040 molar. This is calcium chloride. The calcium comes from the one source. On the other side here, I have 150 milliliters. This is 2.9 times 10 to the negative 2 molar. This is sodium hydroxide. Again, we'll do the easy question first. 100 mils into 150 mils, the total volume is going to be 250 mils. Sometimes they even throw a small bone in the question here and they just say, oh, what if I mix it and then I dilute it to a final volume of 1 liter? Basically, you take what the final solution is because that's going to end up diluting the solution even more. Because this is a mixing solution, the moles themselves remain constant. We need to do a C1V1, C2V2 for the calcium chloride. We need to do a similar C1V1, C2V2 for the sodium hydroxide side. So let's go start off with the numbers here. Our concentration was 4.0 times 10 to the negative 2 times it by the initial volume of 100. Technically, I should be using liters, but I'm just setting up a ratio here. What's the new concentration given that my final volume is actually 250? Similarly, on the other side, my concentration was 2.9 times 10 to the negative 2. The volume was 150. What's the new concentration given that my final volume, again, is 150? This has nothing to do with saturation. This is just purely when you mix solutions together, the pool is bigger. What is your new concentration upon dilution? So 4e negative 2 times 100 divide 250. This gives me 0.016. That's your concentration of the calcium chloride, CaCl2. On the other side here, 2.9e negative 2 times 150 divided by, 250 here. Total volume here should be bigger. Right. That's why it gets diluted, divided by 250, and this gives me 0.017. Right? And that concentration there is the concentration of NaOH. Okay? So what we're going to do next is we're going to say, well, what I care about here, the salt potentially is going to be calcium hydroxide. They're sort of hinting at that. For that salt on the left side, calcium hydroxide, we need calcium ions, and we have 2 hydroxide ions. What's the KSP? The KSP is calcium times the hydroxide squared. Again, every now and then they try to sneak in, oh, there's a 2, double, or whatever. I may have had to double the numbers, not in this question, but in general, there shouldn't be numbers inside the square brackets. That's always wrong. Okay? So I write these 2 expressions out here. These are 2 totally independent equations. The calcium chloride would be a 1-to-1 ratio with the calcium. So if calcium is 0.016 molar, I know the calcium that breaks off from there is 0.016. That is the calcium concentration, 0.016. Where does the hydroxide come from here? The hydroxide comes from NaOH. We get Na plus and we get OH minus here. This is 0.017. Yes, we are going to get some spectator sodium here. Don't really care about it. I only care about the hydroxide. I get 0.017 molar hydroxide. Again, here, be careful. I'm telling you the hydroxide is 0.017. You don't suddenly double it just because there's a 2 in that ratio there. I've gone in with a meter here and I've actually figured out it's actually 0.017 of my hydroxide. So there's my number there. Whenever you have these 2 numbers, you're ready to punch it directly into KSP. Again, it's a question mark. I don't know whether these numbers are high enough. I'm just going to call it TIP instead, or trial value. My trial value, currently my calcium upon dilution, 0.016. My hydroxide upon dilution, 0.017. I still have to square it. My trial value is currently 0.016 times this 0.017 squared. I'm getting 4.8 times it by 10 to the negative 6. Okay, so that's my trial value. That's currently what my equilibrium constant would look like. My trial value here of 4.8 times 10 to the negative 6, this time is actually a little bit less than this 5.6 times 10 to the negative 6. Not by much, but enough. So in this case here, I can make a conclusion. Our Q value, our trial value, which is 4.8 times 10 to the negative 6, it was supposed to hit KSP. KSP is actually 5.6 times 10 to the negative 6. Because my value is too low, since my trial value is less than KSP, we already know the conclusion is no precipitate. Let's make sure, because I need to hit KSP before I hit precipitate. Let's see if we can go over the explanation again here. Q is supposed to be product over reactant. Currently, after you've done the dilution, unfortunately the amounts, the concentration of calcium and hydroxide left over are a little bit too tiny. Because they're too tiny, the Q value needs to get larger. For this fractionator to get larger, I need to increase products and decrease reactants. For me to increase products, I need to end up with more products. To have more products, I need to shift the equilibrium over. So basically, when I mix the solution together, I had added in calcium, I had added in hydroxide. These ones here were supposed to be low soluble, they were supposed to solidify out, but my current amounts here aren't large enough to actually hit KSP. I'm going to need to drop in more calcium hydroxide. As I drop in more calcium hydroxide, any precipitate that otherwise would have formed is now going to break up. And that's why any solid that's left over is going to be used to increase the product to try to get me to climb up to KSP, and therefore we have no precipitate forming. Okay? So try out a question or two there. Let me know if you have any problems. Thanks, guys.